Look up on a clear night, far from the glow of any city, and you will see thousands of points of light scattered across the darkness. It feels, in that moment, like you are seeing the universe, like the sky above you is a window thrown open onto everything that exists. But here is a truth that took us centuries to uncover, and one that still unsettles me every time I sit with it. What you are seeing, what any telescope on Earth will ever be able to see, no matter how powerful, no matter how far into the future our technology advances, is a thin, glowing sliver of a cosmos that is almost entirely and permanently beyond our reach. Most of the universe is not just unseen, it is unseeable. Not because our instruments are too weak, but because of the very structure of space and time itself. Tonight, I want to walk with you through why that is true and what it means for how we understand our place in the cosmos. To get there, we have to start with two ideas that feel, on the surface, like the most obvious things in the world: space and time. We walk through space every day. We watch time pass on a clock. They seem like the stage on which the universe performs its play, fixed, absolute, the same for everyone, everywhere. That was certainly what Isaac Newton believed, and for more than 200 years, it was the foundation of physics. Newton imagined space as an infinite, unchanging container, and time as a river flowing at the same steady rate for every observer, whether you were standing still or racing through the heavens. It is a comforting picture. It is also, we now know, wrong. The person who overturned this picture was, of course, Albert Einstein, and the way he did it is one of the most beautiful stories in the history of human thought. Einstein began not with some grand cosmic mystery, but with light. In the late 19th century, physicists had discovered that light travels at a fixed speed, roughly 186,000 miles every second, and that this speed does not depend on the motion of whatever is emitting it. That sounds like a small technical detail, but Einstein realized it broke something fundamental. If you are riding in a car and you throw a ball forward, the ball's speed, as measured by someone standing on the sidewalk, is the sum of your car's speed and the ball's speed. That is common sense. But light does not behave that way. If you are in a spaceship moving at half the speed of light and you shine a flashlight forward, someone watching from a stationary point does not measure the light moving at 1.5 times the speed of light. They measure it moving at exactly the same speed as always. Light simply refuses to obey the rules that every other object in our experience follows. Einstein took this strange fact seriously, more seriously than anyone before him, and he asked what the universe would have to look like for this to be true. The answer he arrived at in 1905 was radical. Space and time are not separate, independent things. They are woven together into a single fabric, what we now call space-time. And the way that fabric stretches and compresses depends on how fast you are moving. If light speed is to remain constant for everyone, then space and time themselves have to flex. Someone moving quickly relative to you will experience time passing more slowly, from your point of view, and will measure distances as being shorter along their direction of motion. This is not an illusion, not a trick of measurement. It is a real feature of the fabric of reality. Clocks on airplanes, clocks on GPS satellites, actually run at very slightly different rates than clocks on the ground, and we have to correct for this every single day, or your phone's map would drift off by miles within hours. 10 years later, Einstein went further, and this is where the story becomes truly cosmic. His first theory, special relativity, applied to objects moving at constant speeds. But what about gravity? What about acceleration? In 1915, Einstein published General Relativity, and in it, he proposed something that still, after more than a century, has the power to take your breath away. Gravity, he said, is not a force reaching out across empty space the way Newton imagined it. Gravity is the curvature of space-time itself. Picture a stretched rubber sheet and place a heavy ball in the middle of it. The sheet dips and curves around that ball. Now roll a marble nearby, and instead of moving in a straight line, it curves inward, spiraling toward the heavy ball. Not because some invisible hand is pulling it, but because it is simply following the curved shape of the sheet beneath it. That is gravity, in Einstein's picture. The sun does not reach out across 93 million miles and grab the Earth. The sun bends the fabric of space-time around itself, and the Earth in its orbit is simply following the straightest possible path through that curved geometry. This idea that matter and energy tell space-time how to curve and space-time tells matter and energy how to move is the foundation of everything we now understand about the large-scale structure of the universe. It is why black holes exist, regions where space-time curves so extremely that not even light can escape. It is why we detect gravitational waves, ripples in the fabric of space-time itself, spreading outward when two black holes collide, stretching and squeezing the space between us by less than the width of a proton, and yet we have built instruments sensitive enough to catch them. And it is the starting point for understanding the single strangest fact about our universe, the fact that will lead us to why most of it is forever hidden from view. That fact is this: the universe is expanding. In the 1920s, the astronomer Edwin Hubble, studying distant galaxies, noticed something remarkable. Nearly every galaxy he observed was moving away from us, and the farther away a galaxy was, the faster it appeared to be receding. This was not what anyone expected. The prevailing assumption, even one that Einstein himself had initially held, was that the universe was static, unchanging, eternal. Einstein had actually added a fudge factor to his equations, a so-called cosmological constant, specifically to cancel out the expansion his own theory predicted, because he could not believe the universe was anything other than fixed. He later called this his greatest blunder, because Hubble's observations showed that the universe truly is growing, that space itself is stretching, carrying galaxies apart from one another like raisins in a rising loaf of bread. Run that expansion backward in time, and you arrive at a moment, roughly 13.8 billion years ago, when everything we can observe, all the matter and energy that fills the night sky, was compressed into an unimaginably hot, dense state. This is the Big Bang. I want to be careful here, because the name conjures an image that is a little misleading. It was not an explosion happening at a point in space, the way a bomb detonates in a room. It was the expansion of space itself, everywhere, all at once. There was no center to the Big Bang, no outward edge you could stand beyond and watch it happen, because space itself came into being as part of that event. Asking where the Big Bang happened is a little like asking where north of the North Pole is. The question does not quite make sense because the very framework you would use to answer it did not yet exist. In the earliest fractions of a second, the universe underwent what we call inflation, an incomprehensibly rapid burst of expansion where space stretched by a factor of maybe 10 followed by 25 zeros in less time than it takes light to cross an atomic nucleus. Inflation smoothed the universe out, which is why, when we look at the cosmic microwave background, the faint afterglow of the Big Bang that still bathes the entire sky, we find it remarkably uniform in every direction, to 1 part in 100,000. That uniformity is a fossil, a leftover imprint of that first violent stretching. And then, after inflation, the universe continued to expand, more gently, cooling as it did, allowing particles to form, then atoms, then, hundreds of millions of years later, the first stars, then galaxies, then, eventually, us. Now here is where we arrive at the heart of tonight's question. If the universe has been expanding for 13.8 billion years, you might think that the observable universe, the sphere of space we can see around us, has a radius of 13.8 billion light years, since light has had exactly that much time to travel to us. But it is actually larger than that, about 46 billion light years in radius, because the space through which that ancient light has been traveling has itself been stretching the nose its entire time it was en route. And here is the truly strange part. The expansion of space is accelerating. In the late 1990s, 2 independent teams of astronomers studying the light from distant exploding stars called supernovae discovered that the expansion of the universe is not slowing down under the pull of gravity, as everyone expected. It is speeding up. Something is pushing space apart at an ever-increasing rate, and we have given that something a name, dark energy, even though, and I want to be honest with you about this, we do not actually know what it is. We know how it behaves. We have measured its effects with exquisite precision, but its fundamental nature remains one of the deepest open mysteries in all of physics. This acceleration is the reason most of the universe is, and will forever remain, hidden from us. Think about what it means for space itself to stretch at an accelerating rate. There are galaxies out there, right now, that are receding from us faster than the speed of light. That does not violate Einstein's speed limit because nothing is moving through space faster than light. Rather, the space between us and them is expanding so quickly that the distance grows faster than light can cross it. And because the expansion is accelerating, more and more galaxies are crossing that threshold, moving beyond the point where their light could ever reach us with each passing year. There is a boundary called the cosmic horizon, beyond which light emitted today will never, not in a trillion years, not in any amount of time, arrive at Earth. Everything beyond that horizon is receding from us faster than the light it emits can close the inner gap. It is not that we lack the technology to see that far. It is that the very geometry of an accelerating universe makes it physically impossible, now and forever, for that light to reach us. And it gets more sobering still. Because the expansion is accelerating, that horizon is not fixed. It is closing in. Galaxies that we can see today, that we can study with our telescopes right now, will, over unimaginably long stretches of time, tens of billions of years, cross that horizon and vanish from our observable reach forever. Their light will grow fainter and more redshifted, stretched out by the expanding space it travels through, until eventually it fades below any threshold we could ever detect. If you imagine an astronomer 100 billion years from now living on a planet somewhere in what remains of our galaxy's neighborhood, they would look up at the sky and see almost nothing. The cosmic microwave background would be so redshifted as to be undetectable. The galaxies beyond our own local cluster would have receded past the horizon entirely. That future astronomer might reasonably conclude that the universe consists of a single galaxy alone in an eternal, static void, with no evidence at all that a Big Bang ever happened, no evidence of expansion, because every clue would have been carried beyond the reach of light itself. It is a humbling thought that the very cosmological insights we have worked so hard to uncover might be windows that close, that future generations, however advanced, might live in a universe that has erased the evidence of its own origin. This is why I find it so important that we are having this conversation now, in this particular sliver of cosmic time, when the evidence is still visible, still within reach of our instruments. We happen to live at a moment when the observable universe still contains enough of its own history to be legible. That will not always be true. Now, if the visible universe is only a fragment of what actually exists, a natural question follows. What lies beyond the horizon? Is it more of the same, more galaxies, more stars, stretching on forever? Or does something change out there, something fundamentally different from what we know? This is where physics starts to brush up against speculation, but it is speculation grounded in real mathematics, real theory, and it leads us to one of the most ambitious ideas in modern science, string theory. Here is the problem string theory was built to solve. We have two extraordinarily successful theories describing the universe. General relativity describes gravity and the large-scale structure of space and time, and it works beautifully for planets, stars, galaxies, the expansion of the cosmos itself. Quantum mechanics describes the behavior of particles at the smallest scales, electrons, photons, quarks, and it too works with breathtaking precision, predicting the outcomes of experiments to more decimal places than almost any other theory in science. The trouble is, these two theories do not get along. When you try to apply the smooth, continuous geometry of general relativity to the jittery, probabilistic world of quantum mechanics, particularly in extreme environments like the center of a black hole or the first instant of the Big Bang, the mathematics breaks down. It produces nonsense, infinities that should not exist in a sensible physical theory. String theory was an attempt to heal that rift, and it starts with a wonderfully simple proposal. What if, at the deepest level, the fundamental building blocks of nature are not point-like particles, as we have long assumed, but tiny, vibrating filaments of energy, strings, but so small that even our most powerful instruments could never directly observe their extent. According to this idea, an electron is not a dot, but a string vibrating in one particular pattern. A photon is a string vibrating in another pattern. A quark, yet another pattern. Just as a violin string can produce different musical notes depending on how it vibrates, the strings of string theory can produce different particles depending on their vibrational operator. It is, in a very real sense, an attempt to find the fundamental music of the universe, a small set of vibrating strings whose different notes give rise to everything we call matter and force. What makes string theory remarkable, and also deeply strange, is what the mathematics requires in order to work consistently. When physicists worked through the equations, they found that a universe built from vibrating toy strings does not fit comfortably into the 3 dimensions of space we experience and plus 1 dimension of time. The mathematics only holds together without producing contradictions or negative probabilities if the universe actually has additional spatial dimensions in some versions of the theory, 6 extra dimensions, for a total of 9 dimensions of space and 1 of time. That is an extraordinary claim. Where are these extra dimensions? Why do we not see them, or bump into them, or experience them in any way in our daily lives? The proposed answer is that these extra dimensions are curled up, compactified into shapes so extraordinarily small, on the order of the Planck length, roughly 100 billion times smaller than a proton, that we could never perceive them directly. Imagine a garden hose seen from a great distance. It looks like a one-dimensional line, but get close enough, and you discover it actually has a second dimension, wrapped around into a tiny circle. Something similar might be happening throughout all of space. At every single point in the 3 large dimensions we experience, there might be a tiny, curled-up geometric shape, a 6-dimensional space folded up so tightly that it has remained completely hidden from every experiment we have ever performed. I find this idea both thrilling and humbling because it suggests that the reality we perceive, 3 dimensions of space that we move through so effortlessly, might be an almost superficial layer sitting atop a far richer, far stranger geometric structure. And the exact shape of those curled up extra dimensions is not a minor detail. According to string theory, that shape determines the fundamental constants of nature, the masses of particles, the strengths of forces, the very properties that make chemistry and stars and life possible. A slightly different folding of those hidden dimensions might produce a universe with entirely different physics, perhaps one where atoms cannot form, where stars cannot ignite, where nothing like us could ever exist. This has led some physicists to a genuinely dizzying idea, sometimes called the string theory landscape. The notion that there might be an astronomical number of possible ways for those extra dimensions to fold, that each corresponding to a different possible universe with different laws of physics, and that our universe is just one point in that vast landscape of possibilities. That idea connects directly back to the question of what lies beyond our cosmic horizon because it feeds into one of the more provocative ideas in cosmology today, the multiverse. If inflation, that early burst of exponential expansion I described earlier, happened the way many of our models suggest, then it may not have happened just once. It may be eternal, continuing even now, in regions of space forever beyond our observable horizon, spawning new pockets of space that stop inflating and settle into their own version of a Big Bang, their own expanding universe, and potentially governed by a different folding of string theory's extra dimensions, a different set of physical laws entirely. Our universe, in this picture, would be one bubble among an unfathomable number of others, each key forever cut off from the rest by the same relentless cosmic expansion that is already hiding most of our own universe from us. I want to be honest about the status of this idea. It is not confirmed. It may never be directly testable, since by definition those other regions lie beyond anything we could ever observe. But it emerges naturally from theories that have, in other respects, you remarkably successful, and that tension between mathematical elegance and observational silence is one of the most fascinating open frontiers in physics today. All of this naturally brings us to a question that I suspect has crossed your mind more than once. While listening to me talk about billions of galaxies and countless possible universes, are we alone? Given the staggering scale of even just the observable universe, something like 2 trillion galaxies, each containing hundreds of billions of stars, many of them hosting planets, does it not seem almost statistically absurd to imagine that Earth is the only place life has ever taken hold? I want to approach this carefully, because it is easy to let enthusiasm outrun evidence. Here is what we actually know. We have discovered, at this point, more than 5,000 confirmed planets orbiting other stars, and our surveys suggest that planets are the rule, not the exception, that most stars host at least one. Some fraction of those planets sit in what we call the habitable zone, the range of distances from their star where liquid water could exist on the surface. We have found molecules in the atmospheres of distant worlds, and we are, right now, with instruments like the James Webb Space Telescope, searching for the chemical fingerprints of biological activity, things like oxygen and methane, existing together in proportions that would be very difficult to explain without life maintaining that imbalance. But here is the honest truth. We have not found it yet. Not a single confirmed detection of life beyond Earth. Not a microbe, not a signal, not a single unambiguous sign. And there is a deep, unresolved puzzle, sometimes called the Fermi paradox, named after the physicist Enrico Fermi, who reportedly posed the question over lunch with colleagues in 1950. If the universe is so vast and so old, and life should, by sheer statistics, have arisen many times over, then where is everybody? Why, in all our listening, all our searching, has the sky remained silent? There are many proposed answers, and I find something worth considering in nearly all of them. Perhaps life is common, but the specific jump to complex, intelligent, technological life is extraordinarily rare, a bottleneck we happen to clear, but that most biospheres never do. Perhaps intelligent civilizations are common, but they are short-lived, destroying themselves or transforming into something unrecognizable before they ever develop the means to signal across interstellar distances. Perhaps they are out there, but the distances involved are simply so enormous and our searching so limited, a few decades of radio astronomy compared to billions of years of cosmic history, that we should not expect to have found anything yet. And perhaps, and this is the idea I find most connects back to everything we have discussed tonight, some civilizations might already exist beyond our cosmic horizon, in regions of space now permanently unreachable, their light forever chasing a horizon that recedes faster than it can catch up. If the same expansion that hides most of our universe applies equally to the possibility of life elsewhere, then some of the most interesting neighbors we might ever have had are neighbors we were simply, by the geometry of an expanding universe, never destined to meet. There is something profound in sitting with that thought. We exist in a universe where the very fabric of space places a fundamental limit on what we can ever know, not a limit born of insufficient curiosity or inadequate technology, but one woven into the geometry of reality itself. Most of the universe, whatever wonders or civilizations or physics it might contain, is not merely distant. It is causally disconnected from us, forever, by the accelerating expansion of space. I do not think this should leave us feeling small in a diminishing way. I think it should leave us feeling something closer to awe and even gratitude. We happen to exist at a moment in cosmic history when enough of the universe's story is still legible to us that we could piece together its origin in the Big Bang, trace the curvature of space-time through Einstein's equations, glimpse the ripples of gravitational waves, and even reach, through the abstract, demanding mathematics of string theory, toward a possible unification of everything, gravity and the quantum world, wrapped into a single elegant framework built from vibrating strings and hidden dimensions. That is not a small inheritance. That is the product of centuries of human beings looking up at the same dark sky I described in the beginning of this conversation, and refusing to accept that its mysteries were beyond understanding. So when you next look up at the night sky, I hope you carry two things with you. First, a sense of just how much more there is. Galaxies beyond galaxies, dimensions folded so small we may never directly touch them, entire universes perhaps blooming beyond a horizon that recedes a little further every single day. And second, a sense of appreciation for the particular, narrow, precious sliver of the cosmos that remains open to us here, now, in this brief and fortunate when the universe still allows us to see far enough to ask where we came from and to wonder, honestly and rigorously, what else might be out there. We may never reach most of the universe, but we have reached far enough to know that it is there, and far enough to keep asking the next question. And to me, that has always been the very heart of what makes this pursuit so worth a lifetime, and worth this conversation we have just shared.